Hey, welcome to my electronics channel. In this video, I want to talk about the root mean square voltage and current. But first, before I talk about root mean square voltage and current, I want to talk about the effective voltage and current. And as it turns out, those two concepts are the same. Basically, the effective voltage or current is the voltage or current in DC that would do the same amount of work that a given time varying voltage or current does. And the way that we're going to explore this idea of effective voltage or current, and we'll just focus on effective voltage, but the idea of current is going to be pretty much identical, is by looking at a simple system where I have an AC source connected to a simple resistive load. So this AC source is a time varying voltage and it's connected to a resistor of some kind. We are going to assume that this time varying voltage is sinusoidal. So it's going to look something like that. And since we're trying to come up with an effective voltage or current, or the equivalent voltage or current in DC, that would do the same amount of work that this particular circuit does, we want to go and look at how much power is being dissipated in this circuit. If this was a DC circuit, then the power would be equal to the voltage squared over the resistance. Since this is an AC signal, we can look at power as a time varying value, and that's equal to the time varying voltage squared over the resistance. So what does this V of t squared look like? Well, it's going to be sinusoidal, but it's going to look like that. It's going to be at twice the frequency of V of t, and it's going to be all positive values. So if this is my V of t squared, my P of t, or my power over time, is going to be the exact same shape, but it's going to be scaled by the resistor. So it's probably, assuming that resistor is bigger than 1, the amplitude of it is going to be less than what I have for the voltage. Typically when I'm talking about power, I want to know what the average power is, not the time varying power. And this is also important when you're comparing an AC to a DC, because a DC, the power is going to be constant, but in an AC system, you want to know what the average power is since it's going to be changing. So to get this average power, what I'm going to want to know is what is the average of this squared voltage signal. And the way that I can do that is I can take the area under the curve and then divide by the total time of, in this case, 1 period. So given the initial, this is the initial voltage, then 1 period is going to occur over this time. So if I take the area under the voltage squared curve and divide by the period, that is going to give me the average of that voltage. And that's going to look like this. 1 over t, so dividing by the period, dividing by that time, and then taking the integral from 0 to t, so it's the area under the curve from time 0 up to 1 period of the squared voltage, and I'm doing this over time. So that's the average of my squared voltage, and I divide by R, that's going to give me the average power. And referring back to the DC power that we were wanting to compare to, the DC power is going to be some voltage squared over R, and I'm talking about some effective voltage or current for an AC circuit. So this right here is the V squared, or the V effective squared over R. So this whole numerator is the effective voltage squared. So if that's the effective voltage squared, then the effective voltage will simply be the square root of that. The effective voltage is equal to the square root of 1 over t times the integral from 0 to t of v squared of t dt. This effective voltage is calculated by taking the square root of the mean of the square of the voltage. In other words, it's the root of the mean of the square. So the more common term for this effective voltage is the root mean square voltage, or more commonly RMS voltage, where RMS stands for root mean square. So the root mean square voltage is the equivalent DC voltage that would dissipate the same amount of power as the AC signal is dissipating or generating. Since we are typically going to be dealing with voltages and currents that are sinusoidal, we usually are not going to have to do this calculus. We won't have to do these integrals, because it turns out that for sinusoidal signals, when you do this integration and the averaging and the square root, it turns out that there's a very simple equation for relating the RMS voltage back to the original V of t. And I'm going to show you a non-calculus way of relating the RMS voltage back to the V of t here. Okay, let's assume that we're back to the system with a voltage source connected to a resistive load that's generating some amount of current. And let's say that V of t, it's sinusoidal with some peak voltage and some frequency omega. I of t is in phase with the voltage, has some peak voltage, IP, and the same frequency, omega. To calculate power, we multiply voltage times current. So that'll be Vp sine omega t times the peak current, IP, sine omega t. Now if we multiply this out, I get Vp times IP times sine squared omega t. And with a trigonometric identity, we can turn this sine squared omega t into 1/2 times 1 minus cosine of 2 omega t. Let's distribute this VPIP and this 1/2 through these two terms, and we'll end up with two terms. We'll get VPIP over 2 minus VPIP, peak voltage times peak current, over 2 times cosine of 2 omega t. So this overall expression is the time varying power. And we can look at two components to this time varying power. There's a constant component and the varying part. And if you typically don't care about the time varying power, you care about the average power. So looking at the average power, the average of a cosine expression is going to be 0. So if we're calculating average, that whole part goes away. And the average of a constant is simply going to be that constant. So it's just splitting out the average. Getting the average power is equal to Vp times IP over 2. And if we split this up into a voltage part and a current part, we get Vp over root 2 times IP over root 2. And remember, when we're talking about average power, we can compare this back to a DC equivalent. So the DC equivalent, we can look at this part being the voltage DC equivalent and this part being the current portion of the DC equivalent. So, and remember that DC equivalent, or the effective voltage and the effective current, are also the RMS voltage and the RMS current. So this can lead us to the conclusion that the RMS voltage, or the effective voltage, is equal to the peak voltage over the square root of 2, and the RMS current, or the effective current, is equal to the peak current of that AC sinusoid over root 2. In North America, the typical house voltage in a house is 120 volts. This is an RMS voltage. Since the voltage to a house is an AC signal, there's an AC voltage, plotted over time, it's going to look like this. if this 120 volts is the RMS, that means that this VP, this peak voltage, is going to be, well, rearranging this equation, is going to be the RMS times root 2. So 120 volts times the square root of 2, which works out to be about 170 volts. So the house voltage, even though it's stated as 120 volts, it actually goes up to a peak of about 170 volts and down to a negative peak of about minus 170 volts. So that gives you a bit of insight into where RMS voltage and currents come from, and I'll see you in the next video. I actually don't know how the rest